The World Health Organization cites antimicrobial resistance as a major threat to global health, food security, and development. Current antibiotics are becoming less and less effective, a problem exacerbated by years of misuse. One obvious way that we can combat the rise of antimicrobial resistance is the development of new antibiotics whose effectiveness can be preserved with responsible stewardship. This brings us to the focus of our research, Paenibacterin, a novel, broad-spectrum lipopeptide antibiotic isolated from the soil bacterium Paenibacillus thiaminolyticus by researchers at Ohio State University. The mechanism of action of Paenibacterin is similar to that of polymyxin B, which should be familiar to everyone as a component of a popular over-the-counter topical antibiotic cream. It works by disrupting bacterial membranes, causing leakage of intracellular contents and depolarization, resulting in cell death. But where polymyxin only acts on bacteria with a lipopolysaccharide-containing membrane, Paenibacterin exerts its activity against a broad range of bacteria both with and without. This makes Paenibacterin a promising candidate for antibiotic development. But first, the mechanism of action must be further understood. This is complicated by the fact that Paenibacterin contains no intrinsically fluorescent amino acids, which are used to study the interaction of peptide antibiotics with membranes. To address this, we have developed a method for the total synthesis of Paenibacterin using solid-phase peptide synthesis. We have used this approach to prepare variants of Paenibacterin containing fluorophores that will be used to further investigate the mechanism of action and address the following questions. First, besides lipopolysaccharides, what membrane components are targeted by Paenibacterin? Does Paenibacterin accumulate in the cell interior? Are there specific intracellular targets? Does Paenibacterin aggregate in the membrane or exert its bactericidal activity through the formation of specific structures such as a nanopore? To answer these questions, we have synthesized a 7-dimethylaminocoumarin-derived amino acid. This amino acid can be incorporated into peptides and exhibits an increase in fluorescence as it enters a hydrophobic environment, such as the interior of a bacterial membrane. Using a coumarin-Paenibacterin analog, we will be able to identify membrane targets by varying the composition of model cell membranes in the form of small unilamellar vesicles ranging from 15 to 30 nanometers, and monitoring an increase in fluorescence as the peptide inserts into the lipid bilayer. Similar techniques have been used to study other lipopeptide antibiotics. In these cases, the fluorescence of the common amino acid, tryptophan, was used, but this coumarin amino acid should exhibit greater sensitivity and should be observable in studies on live cells that contain their own tryptophan. Confocal microscopy at sublethal concentrations of our probe should allow us to identify intracellular targets of Paenibacterin through co-localization with other fluorescent dyes. Other modifications will allow us to determine the proximity of Paenibacterin molecules in the membrane, searching for the formation of aggregates or pores. It is our hope that an understanding of Paenibacterin's mechanism of action will allow for the development of a new, clinically useful broad-spectrum antibiotic. Thank you.